Welcome back to the discussion of spatial computing. Today we are going to meet Dr. Betsy George at Oracle Spatial and learn from her the excitement of spatial computing at Oracle, a popular product which we have mentioned several times in this course. Okay? So please say hello to Dr. Betsy George.
Hi.
Hi. So Betsy, the first question we wanted to ask you is, coming from a broad mathematics and computer science background, how did you get started with spatial computing?
I came into spatial computing through my interest in graph theory. So graphs, I have always been impressed with the expressiveness and the simplicity of the model called graph. And so I got introduced to graphs at the very early stage. And then when I was started my research, I was looking for some real world applications of graphs. So then I got introduced to transportation networks, which are basically spatial networks. And my first familiarization with transportation network was through a study of evacuation planning algorithms. And so when I studied the problem a little bit, I realized the challenges that the real world application domains brought to this world of graph theory. And I was really excited and impressed by the way we needed to reevaluate the algorithms in terms of the assumptions that we made when we designed graph algorithms. We needed to reformulate them to suit the applications better. To be more specific in terms of the evacuation planning algorithm, the aim was to evacuate the people as fast as possible. So from the graph theory perspective, that would immediately let me choose the shortest path or the fastest path algorithm and apply that. But then I realized that that's not going to work because the roads have capacities and you cannot push everybody to move along the same shortest path possible from the source to the destination. So we needed to take care of the capacity constraints, which was not really taken into account in any of the shortest path algorithms that I knew of. So that was one example where graph theory really met the real world application, and that opened up a lot of possibilities for interrogation of the assumptions that were behind the graph theory algorithms. So to put it shortly, I became interested in spatial computing through spatial networks. And so then I started seeing the lot of challenges that are raised by when you bring location into computations, and how to effectively use that. And so it's been a really exciting journey, which started off with spatial networks, which are like the road networks.
Oh, wonderful. So in this course, we did discuss shortest path.
Okay.
And I'm guessing a lot of people in this course have used services like Google Maps or other GPS devices to find shortest path.
Sure.
So it may be nice to kind of briefly, revisit the evacuation scenario. So let's say everybody living in Boston had to leave because of a major hurricane.
Sure.
And if they all just went to Google and found shortest path to their destination, maybe in New York City or in Albany, what would go wrong? I mean, why not do that?
Oh, you will see like cars backed up all the way to the place where you started, because everybody is going to drive out, and if you ask them to move along the fastest route possible, then everybody is going to be there, and the roads will get congested and the traffic will get backed up. So you had to take care of the capacity as the roads get used more and more. The congestion increases, the traffic time, the travel time gets increased. So the fastest path itself changes based on that. So that had to be taken into account. So so that added a new dimension to the shortest path algorithm. So
neat. So I guess graphs have been extended to model edge capacity as well. So is there like a general family of graph models which take capacity into account?
Yes. For example, my research was actually to look at the changes that the graph can the whole assumption that the graph can change as the network is getting used, and so the temporal changes that happen to the graph needed to be taken into account in the algorithms themselves. Like, so when you do the computation, you have to keep track of the changes that take place to the graph. So that brings in the the temporal graph concept. And so the algorithms needed to be re-examined in that light.
They're wonderful. And I think your encyclopedia article on road networks is going to be one of the supplementary readings.
Okay.
So hopefully some of the students will relate back and they can see the temporal part also that you brought it. Wonderful. So the next question, what kinds of things are you working on nowadays at Oracle Spatial? And could you also tell us a little bit more about Oracle Spatial from, as perspective of somebody working in the group?
So Oracle Spatial basically, provides support for Oracle, the spatial data types. We do have spatial data types. We do support multiple coordinate systems and most commonly used spatial operations, like you can find nearest neighbors, you can, the fastest route from point A to point B and stuff like that. And also we do have, as a part of the Oracle Spatial, we do have a visualization tool called Map Viewer, which is being extensively used to visualize maps and any spatial data for that matter. And I specifically work in the network data model team. So I was kind of fortunate enough to find a job which actually makes use of my research and could actually carry my research into the industry. So I work in the network data model team, and the network data model basically provides the facilities to represent networks or graphs in the database. So there is a database representation for networks. And on top of that, there are analysis capabilities provided, so most of the most commonly used graph operations are being offered. Like we can compute shortest path. We do traveling salesman problem. And then we do have the network equivalents of the most spatial operations, like you can find nearest neighbors within cost analysis, drive time polygons, all based on network costs. So that is the basic thing that our group does. So what my specific work has been, again, the adding a temporal dimension to the data model, which didn't have a time aspect to it before. So making the graphs time aware and the network computations time aware actually opens up a lot of possibilities. For example, for the simplest case would be a traveling salesman problem. And when you use them as computing a trucking route to visit 4 cities, if the application is time aware, then we can actually insist that the trucker visit a certain city in a certain period of time. And sometimes that becomes a necessity.
Like to avoid rush hour and so on.
Yes, there are rush hours, and also there are some there are some restrictions, like you need to visit this particular place on a certain day. So you can actually incorporate that constraint if the application is time aware. Then, as we mentioned earlier, the other application would be incorporating time in such a way that the graph itself is modified and handled in such a way that it can change. So the graph changes with time. For example, the congestion. So traffic data is out there now, so we do have the facility to incorporate the changes in the traffic volume as during at different times of day. And based on that, the travel time changes. So we can actually compute the fastest time if you start at 8 a.m. in the morning.
Oh, wonderful.
Versus midnight. And you might even get 2 different routes when you compute these 2 different routes at 2 different times.
Wonderful.
So I am basically focusing more on the temporal aspect of the network data model. We also have a little bit of a support for multimodal routes, which again brings in time because everything is schedule based.
They are wonderful. So you already kind of gave answer to the next question I was going to ask, which was, so you remember chapter 6 in the spatial database book, which had a very basic model of transportation networks in terms of graphs. So the basic question was, when you see the graph model or the spatial network model in Oracle Spatial versus what you see in the academic textbooks, what are the things which are common and what are the things which are different?
The basics are basics are very common. We do have nodes and edges or nodes and links, so we do have entities which are represented by nodes, like which could be like intersections of roads or like cities.
Okay.
And also like we do have connections between nodes. They can be any relationship. So in the case of a road network, if one node is reachable from another node, we connect them using an edge or a link. So in the basic network data model in Oracle also, like we do have node table, which is a database representation of nodes, and the link table, which actually provides the connectivity between nodes. But right now, the thing is like, the textbook model actually treats the graph as static. Nothing changes. So you do have one edge between node 1 and node 2, and you actually have one parameter called cost on that link. So the underlying assumption is that the cost doesn't change. But we do have a mechanism right now to actually represent the cost in such a way that it actually shows a variation with respect to time.
Wonderful.
So that is one of the most striking differences I would say it has.
Wonderful. And I think your encyclopedia article gives a little glimpse of that.
Sure.
Wonderful. Now looking ahead, next 5 to 7 years, what are the major directions in Oracle Spatial and in your own networks module?
I think when I think about it in a very very generic way, I think like to go more on to kind of like expand more on this changing graph paradigm. People are collecting data everywhere, and if you use an online navigation system, like everybody's like saying that, okay, fine, don't take this road because it's congested, and like this is the travel time, and so and big companies like Nokia is like putting data out there. So there is a lot of data coming in, and so we need to somehow incorporate this into our computations to make computations more meaningful. So I think we need to have a mechanism to somehow use this data meaningfully, but at the same time, the volume is like growing like so drastically. So we need to somehow make the computations efficient. So I think big data is here, so that I think that is going to sort of like creep in everywhere. So we need to explore that and how we can actually incorporate the big data analytics into network computation, which is not that easy because networks are not that easily partitioned, sensibly. So we need to figure out how to partition networks, sensibly, so that we don't have too much communication going on between the nodes, and also we don't sacrifice too much of accuracy. Mining is a different issue because I think mining, as long as we find out the trends, it's okay. But with networks, it's still a tough problem how to do that. So, and then also like we need to adapt our algorithms also to suit this big data paradigm. We need to figure out how to do that. And even if we don't move into that, as the volume of the data increases, it is basically, and also even just bringing in time kind of complicated everything.
Right. You explode the data volume, right? For each instant you may have a replication of the network, right?
Yeah. And so it is basically, and also like, we cannot apply the old algorithm techniques. Most of the assumptions that we made with respect to the old algorithm design cannot be applied when time comes in, because most of the properties that we relied on to apply these techniques are breaking. And for example, I cannot use dynamic program to find the best shortest path, or rather to answer the question when to start.
Oh, wow. So we did talk about Dijkstra and A stars. So, so what happens to those when you add time?
Because Dijkstra basically depends on a property called greedy property, and which actually depends on a suboptimal structure, of the final solution, which breaks when we actually extend the shortest path question to when is the best time to start so that I spend the least time on the road. So we are actually talking about optimizing it across on the graph and across time too. So when that comes in, the greedy property is not satisfied anymore. So I cannot extend Dijkstra easily.
Wonderful. Sounds like a lot of interesting opportunities and in the area or the room for this area to grow.
Yes, for a researcher, yes.
Wonderful. So thank you so much, Betsy, for taking the time to talk to our audience. And you are in really a sweet spot where you can look at the research and also you can bring it to an influential product, which is now being used by very, very large number of people. So,
Thank you, Professor Shekhar, for giving me this opportunity. This was just an honor, great honor to be a part of this project.
they are
Thank
wonderful.
you.
Thanks.
Thank you.
Wonderful. So this was Dr. Betsy George, a principal, member technical staff at Oracle Spatial, and a lot of things she talked about we covered in the module on spatial network. And this is a field which already has many applications, and as you heard, looks like there will be many more in coming years. And hopefully, some of the people in this course would be participating in shaping this field in the near future. Thank you. And next interview, we'll meet few other researchers in this area.